Nodal analysis is a very efficient way to analyze circuits. It is based on the KCL, Kirchhoff current law. To apply nodal analysis, we need to know nodal voltage. So let's use this circuit to illustrate the steps of nodal analysis. In this circuit, there's a current source here, and all of these resistors R1 to R5. And how many nodes we have at here? 1, 2, 3, and total 4 nodes. So in these 4 nodes, one of the nodes needs to be defined as a reference node, one of those, and which is ground node. And you can pick any nodes in the circuit as a reference node. And here, normally here, and for convenience purpose, people normally choose the nodes at the bottom of the circuits as the reference nodes, also known as a ground node. So at the ground here, ground node, the voltage at the ground node equals 0 volt. So this is very important, and this is assumption here. This is assume this node is a ground. You can use this node as a ground, but it's not convenient to analyze. So normally people use the nodes in the bottom of the circuit as a ground node. Once we define the reference nodes here, that's our reference node, and then we need to define nodal voltage. So nodal voltage is the voltage at each node. Here I use different color. At each node here with respect to the reference node. Okay, since the voltage at the reference here is 0, we will use V1 to indicate the voltage at node 1 with respect to the reference node, and V2 at the voltage of node 2 with respect to the ground. We do not write V1 0. So here, this is node 0, this is node 1, this is node 2, this is node 3. We do not write V1 0, V2 0. Instead, we just write V1 and V2. So step 3, we need to mark the branch current. So all the current flows through each branch. And regarding the direction of the current, that's your choice. Each individual has different choice. So next step is to use KCL in each node. The current flow into a node is equals current flow out of the node. So current flow into, that's I, and current flow out to, I1 and I2. So that's the KCL on node 1. Let's look at node 2. Current flow into, that's I2, and current flow out to, I3 and I4. And node 3, current flow into, that's I4, current flow out to, that's I5. This step is to apply KCL for every node, but we do not consider this reference node. Reference node, just reference. We don't need to apply KCL on the reference node. Next step is to use Ohm's law to express the branch current as a function of the node voltage, because our goal is to solve the node voltage when using nodal analysis. Essentially, we need to convert all this current as a function of nodal voltage. So let's look at here. What is I1? I is a given. I is a, that's a constant. That's a current source. That's a constant. It's a given. 10 amp, 20 amp. This is a given. I1 is this. That's the voltage along this resistor divided by this resistor. V1. That's the node voltage. That's the voltage on this node. With respect to this node. So this is V1 is exactly the voltage on this resistor R1. So what is the sign of V1 here? Basically here this is positive, this is negative. Okay, so I1 equals to V1 divided by R1. It minus 0 because this is the ground. The voltage at the ground is 0. Let's look at I2. The node voltage here is V1 and V2. They are all respect to this common ground here. So what is the branch voltage on R2? So like here, this is minus here, VR2. VR2 equals to V1 minus V2. The sign is defined, this is positive, this is a negative. So what is I2? I2 is V1 minus V2 divided by R2. Okay. So we use the same thing as I3 and I4 and I5, all of those. I3 is V2, the voltage on node 2 divided by R3. So I3 is V2 divided by R3. So what is I4? I4, that's the voltage on R4 divided by R4. So what's the voltage on R4? V2 minus V3. So V2 minus V3 divided by R4. So that's I4. What is I5? I5, that's the branch current flowing into this resistor. So what's the voltage on this resistor? That's V3. So what is I5? I5 is V3 divided by R5. From here, we can see we have 3 node voltages, V1, change another color, V1, V2, and V3. How many equations? 1, 2, 3. So we have 3 equations, we have 3 unknowns. Basically, the problem is solved. We can use these 3 equations to solve V1, V2, and V3. After we solve V1, V2, V3, we can obtain all the currents on each branch. The circuit analyzed completely. So in terms of how do we solve these equations, we can write these 3 equations organized in the matrix form. We can use mathematical tools to obtain the solution very easily. So let's see how do we do that. First of all, we want to write this equation as AX equals to B. It's a matrix vector. In this case here, I'm going to write A is a matrix and V1, V2, V3. Okay, and then what's the B here? B is I, 0, and 0. Next is just figure out what's the matrix A. Matrix A, that will be 3 by 3. The first coefficient will be regarding V1, R minus, I'm going to use R minus 1, reduce the space here. And then V2 here, so that's minus R1, R2, minus R2, minus 1, and 0. That's here. And then the second equation here, V1 is only R2 minus 1. I may need a little bit bigger space here. The coefficient R2, that's all of this terms, minus R2 minus 1, minus R3 minus 1, and then minus R4 minus 1. And V3, that's coefficient R4 minus. The last equation, the coefficient of V1, that's 0. V2 minus R4 minus 1. And then V3, there are two terms, minus R4 minus 1 minus R5 minus 1 here. This is our matrix A, V1, V1, V2, and V3. That will be equals to A. You do the inverse, you multiply by this vector, I, 0, 0. This can be easily solved using MATLAB or Octave or any other mathematical tools to solve it.